So what we're going to be looking at today is we're going to be looking at these things called trigonometric substitutions. And basically what they are is they're kind of like U substitutions, except we're going to be using trigonometric values, okay? And we're going to be using some identities for trig values, all right? And the big trick about working with trig substitutions is that we have to recognize the form of the integral in order to recognize that we should be utilizing a trig substitution. All right. So what I'm going to do is I'm going to first start out with the basic form of these trigonometric substitution integrals. Okay, along with the trig identities that are going to inform them. And then once we do that, right, then we'll move into some examples of how we actually go in and do these trig identities. Okay, or trig substitutions, excuse me. Okay, so what we're going to start out with is we're going to start out with looking at our Pythagorean identities. Okay, and so we're going to start out with the first one. We've got that sine squared theta plus cosine squared theta is equal to 1. Okay, and if I rewrite that, what that's going to give me, the one that we're concerned with is cosine squared theta, okay, is going to equal 1 minus sine squared theta. Okay, 1 minus sine squared theta. And if I then rewrite this, if like say for example, I've got something like the square root of 1 minus sine squared theta, then that's going to end up equaling the square root of cosine squared theta because I can make a substitution, and then it'll end up equaling cosine theta. Okay, so that's how that works. All right. In addition to that, we could actually go through and say, for example, that instead of 1 minus sine squared theta, I instead had something like 4 minus sine squared theta, or 4 minus 4 sine squared theta. Okay, and I had that in square root. Well, this would then be the square root of 4 times 1 minus sine squared theta, which would equal the square root of 4 times cosine squared theta, which would then equal the square root of 4 times cosine theta, which is just 2 cosine theta. Okay? And so we're kind of looking at things like this, right? Where we might have some values, we might have some coefficients that we could go in and we could make some changes for, but then inevitably I'm going to make a substitution. I'm going to substitute for 1 minus sine squared theta, I'm going to substitute cosine theta, all right? And then that is going to end up giving me my trig substitution. The next one that we're going to be looking at is we're going to be looking at 1 plus tangent squared theta equals secant squared theta. So in this case, if say for example, I've got something that looks like the square root of 1 plus tangent squared theta, right? Then I can let that equal the square root of secant squared theta, which is just going to end up equaling secant theta, which I can then use something like, well, we do know already what the integral of secant theta is. So that's, a fairly simple integration. All right. On the other hand, we could also have tangent squared theta is equal to secant squared theta minus 1. Okay, so if we have something of the form, right, secant squared theta minus 1 in square root, that'll equal the square root of tangent squared theta, which will equal tangent theta. Okay, so that's basically the idea here. Now what we're going to do is we're going to get kind of clever with our substitutions. And when we get clever with our substitutions, what that's going to allow us to do is it's going to allow us to transform our integral into something that has these trig identities. And once we do that, then we are pretty much home free. So let's take a look at an example now. And what we're going to want to do is we're going to want to look at some canonical examples that kind of show us how it is that we should be working with these trig substitutions. And because basically these techniques, they depend upon the form of the integral. So let's take an example. Let's say, for example, that I have something that looks like this. I've got the square root. I want to find the integral of the square root of 9 minus x squared dx. And what I'm going to do is I'm going to choose the right value of x to substitute so that I can end up back at my, so that I can then go in and substitute for something that I can then integrate. So like, let's say, for example, I'm going to let x equal 3 sine theta. And the reason why I'm going to do that is because what I'll get when I substitute is I'm going to get 9 minus 3 sine theta squared, and that's equal to 9 minus 9 sine squared theta, which ends up equaling 9 times 1 minus sine squared theta, which equals 9 cosine squared theta. Okay? So when I take the square root of it, I'm going to end up at 9 cosine theta, or excuse me, at 3 cosine theta. So I'm actually going to end up with a value that's really going to be a lot easier to integrate. All right, so that's why I chose x equals 3 sine theta. All right, because it's of the form that allows me to then transform this into a single trigonometric function. So let's do that. We're going to let x equals 3 sine theta. And then that means too that dx, my derivative of x, I'm going to need to have something to substitute there in terms of theta, is going to end up equaling 3 cosine theta d theta, because that's the value for, that's the derivative of x. The derivative of 3 sine theta is 3 cosine theta d theta. Okay? So now I'm going to go in and I'm going to resubstitute. Or actually, I'm going to go just substitute. And that's going to give me the square root of 9 minus 3 sine theta squared times 3 cosine theta d theta. Now, this is then going to give me the integral of the square root of 9 minus 9 sine squared theta times 3 cosine theta d theta. This is then going to be the square root of 9 times 1 minus sine squared theta times 3 cosine theta d theta, which is equal to the square root, and now we can make that substitution. That's equal to cosine squared theta. So this is going to be 9 cosine squared theta times 3 cosine theta d theta. And we're going to find that integral. So this is now going to end up equaling 3 cosine theta times 3 cosine theta d theta, which is simply 9 times the integral of cosine squared theta d theta. All right, so the whole point of us choosing our value for x is for us to make that substitution. This substitution in particular right here. Okay, and so in a minute we'll talk about this and we'll generalize it a little bit, but what you want to notice is that if you have something of the form, right, some constant minus an x squared, okay, or some power of x squared, then what you're going to be doing is you're going to be substituting for sine theta, because it'll allow you to transform to our cosine squared theta. All right, and then we can take it out of the square root. So if we have that square root form, that's what allows us to make that substitution. Now we can work with the second part of the problem. As we work with the second part of the problem, what we're going to be doing now is I'm first going to integrate this, the cosine squared theta d theta. And if you remember from our trig integrals, cosine squared theta, okay, is going to equal 1/2 plus 1/2 cosine 2 theta. Okay, and that's the substitution that we'll make. So this is going to end up equaling 9 times the integral of 1/2 plus 1/2 cosine 2 theta d theta. And this will then equal 9 over 2 theta plus 9 over 2 times 1/2 sine of 2 theta plus c. Okay, which if we just rewrite this is going to give me 9 over 2 theta plus 9 over 4 sine 2 theta plus c. Now this is where things sometimes get a little bit tricky. Remember, we don't want our function in terms of theta. We don't want the integral in terms of theta. We need it in terms of x. So what that means is that we are going to have to go figure out what theta is in terms of x. All right. So remember that x equals 3 sine theta. On the one hand, we'll use inverse sine functions, but we're also going to actually have to utilize a triangle for this. Okay. So first, x over 3 will equal sine theta. So that's good, right? Because we have this 9/4 sine 2 theta, but I don't know what sine 2 theta is. I'm going to have to actually also, okay, figure out what cosine theta is and make a substitution. So remember that sine 2 theta is going to equal 2 sine theta cosine theta, which is one of the things that we're going to have to transform this into. So x over 3 is going to equal sine theta, and then I'm going to draw a triangle to find cosine theta. So here's theta. Sine theta is x over 3, so here's x and here's 3. And so using the Pythagorean theorem, this bottom term is going to end up being the square root of 9 minus x squared. Kind of nice that way. If you notice, remember that x squared plus, in this case, b squared is going to equal 3. So b squared will equal, 3 squared, excuse me. B squared will equal 9 minus x squared. So b, our adjacent side, is going to be 9 minus x, the square root of 9 minus x squared. Okay? So that means that cosine theta is going to end up equaling the square root of 9 minus x squared divided by 3. Okay? The last term that I'm going to get is I'm actually going to need to find theta. So I need to find theta because I've got just a theta all by itself. It's not sine theta, it's theta all by itself. So x over 3 equals sine theta. So that means that theta equals the sine inverse of x over 3. So now I can actually do all my substitution. So my integral, the integral of the square root of 9 minus x squared dx is going to end up equaling, and this is going to be 9/2 sine inverse of x over 3 plus, and this will be 9/4 times 2 times first sine theta, which is x over 3 times x over 3 times the square root of 9 minus x squared divided by 3. And plus c. And this will end up equaling then 9/2 sine inverse x over 3 plus, and this will divide out, that'll become a 2. The 3's will cancel, that becomes a 1. So it'll be plus 1/2 x times the square root of 9 minus x squared plus c. So the whole process for trigonometric substitution is somewhat involved, all right? But it is logical. First, we identify the kind of integral that we're working with, okay? In this case, we're looking at an integral where it's the square root of some constant minus an x squared term. And in that case, from this position or from this perspective, that's going to be a substitution for a sine squared term, okay? And once we do that, we'll take that as our substitution. We'll find the derivative for dx, and then we're going to be substituting back into the original equation. Once you do that, then it's a matter of algebra. And sometimes the algebra can get a little tricky, okay? You got to be very, very cautious about how you do your algebra. But then once we do that, what we end up with is a very tidy integral. In this case, it's a trig integral. So 9 times the integral of cosine squared theta d theta, right? And then we go and find that integral. Once we've found the integral, what we want to do is we need to go figure out what theta is equal to, and oftentimes we're going to have to figure out what sine theta is, or cosine theta, or maybe even tangent theta or secant theta, depending upon the kind of integral, all right? So we've got to actually go back and substitute back in for values of x. Take our thetas, turn them into values of x using triangles, okay, and also inverse trig functions. Once we do that, we can resubstitute back in, okay, and do some simplification, and that gives us our entire answer. So the trigonometric form that we're working with, so here's the form that we've got on that last one. That's the integral of what we say the square root of a squared minus x squared dx, where a is a constant. Okay, where a is a constant. And so what we choose here is we're going to let x equal a sine theta. Okay, and so then dx is going to equal a cosine theta d theta. So when we do our substitution, what we'll end up with is we'll end up with the integral of a squared minus a squared sine squared theta times a cosine theta d theta, okay, which is going to equal the integral, and it'll end up being the square root of a squared cosine squared theta, once we actually do our algebra, times a cosine theta d theta, which just ends up equaling a squared, or the integral of a squared cosine squared theta d theta. And so when we have something of that form, that's basically what we're going to be doing. All right, a is some constant. We utilize x equal to a sine theta. We have dx, it will be that a cosine theta d theta, okay? And then that actually ends up giving us our trig substitution, okay? Now, what that also means is, and this is just a generalization, we want to kind of get used to doing these kind of things. That means that if we go in, we're going to let x equal a sine theta, okay? So x over a is going to equal sine theta. Cosine theta will then equal the square root of a squared minus x squared over a. Okay? And theta will end up equaling sine inverse of x over a when we actually do our substitution. All right? And so basically that's what we're doing whenever we utilize a trig substitution. For me, I find actually understanding where the substitution is coming from makes it a lot easier versus trying to memorize the forms. But I always have to remember that this is what substituting in for a sine theta looks like, right? Whenever I have something that has the form, the square root of a squared minus x squared. Okay, so now let's take a look at another example. This one's a bit different. Let's take, for example, that I've got dx over the square root of 1 plus x squared. Okay? Now you'll notice in this case that what we don't have is we don't have an a squared minus x squared term. And so consequently, it doesn't make sense for us to actually utilize x equals, in this case, 1 sine theta. But what this does look like an awful lot like is like this one. Secant squared theta equaling to 1 plus tangent squared theta. Okay? So if you imagine, if you let x equal tangent theta, then what we'll get is we'll get something that will be like secant squared theta, and then we divide. Or excuse me, not divide, but then we take the square root, we end up with secant theta, right? Things get much easier from there. So what we're going to do is we're going to let x equal tan theta, and so dx will end up equaling secant squared theta d theta. And now I can do my my substitution. I now have the integral of secant squared theta d theta on top divided by the square root of 1 plus secant, or excuse me, not 1 plus tangent squared theta. Okay, which is going to end up equaling the integral of secant squared theta divided by the square root of, and this is secant squared theta, and then d theta. So this ends up equaling the integral now of secant squared theta divided by secant theta d theta, and that is just the integral of secant theta d theta. Using our antiderivatives, what we know now is that this is going to equal the natural log of secant theta plus tangent theta plus c. And so now I've actually finished my integration. Now what I need to do is I need to go substitute again. Well, I know that x equals tangent theta, so I know tangent theta is going to be x, so I can make that substitution. X equals tan theta. All right. Now, what I'm going to do then is I'm going to rewrite this. So x over 1 is going to equal tan theta. So what we'll do is we'll actually draw a triangle. Here's my triangle. Okay. And So the opposite side, so I've got theta, the opposite is going to be x, the adjacent is going to be 1, and so my hypotenuse is going to end up being the square root of 1 plus x squared. Okay? So what that means is that secant theta is going to end up being equal to the adjacent, is going to equal the hypotenuse over the adjacent, so it's going to end up being the square root of 1 plus x squared divided by 1, which is just the square root of 1 plus x squared. So now I go in, I substitute back into my equation, and this will end up equaling the natural log of the square root of 1 plus x squared plus x plus c. And that's it. All right, so what we notice, a couple of things as we're going through here, notice that we have something of the form of the square root of, and we could eventually turn it into 1 plus x squared, right? Because that's the case, or 1 plus, tangent squared, which gets transformed into secant squared, right, which we can take out of the square root, right, and we end up with secant theta. Okay, so something of this form that looks like this is going to end up being substituted for x equals tan theta. Once again, we'll utilize our triangles, okay, basically just the Pythagorean theorem and basic identities for trigonometry, okay, in order to substitute back in for theta for x, okay, and that finishes a problem that looks of this form. So let's take a look at it and let's generalize it. So now what we want to do is we want to see, okay, well, if I have something, an integral of the form the square root of a squared plus x squared, okay, a squared plus x squared dx, then what I'm going to do is I'm going to let x equal a tangent theta, okay, and so then dx is going to equal a secant squared theta d theta. When I go in and substitute, and they'll look a little bit different, we'll give some examples in a little bit, this will end up being the square root of a squared secant squared theta times a secant squared theta d theta. And what we'll end up with is, in this very generalized case, we'll end up with the integral of a secant theta times a secant squared theta d theta. Okay, and there we go. In addition to that, what we'll get to, we'll know that we know that x is going to equal a tan theta. So x over a will equal tangent theta. Secant theta, which will be the other one that we see very commonly with this one, is going to end up equaling the square root of a squared plus x squared divided by a. Okay. And theta will end up equaling tan inverse of x over a. All right. Now, depending upon where we see, right, these kind of trig substitutions showing up, we're going to get different kinds of algebra. As you saw in this last one, it didn't look like the first one, right? It wasn't actually what we'd call a straightforward trig substitution. We ended up having to do some further algebra in order to actually take the integral, all right? The big thing to get here is that if I have a square root of this form, I want to try out x equals a tan theta and then proceed from there in order to do the substitution, okay? And utilize my algebra to do that substitution. Because eventually, right, I should be able to get to an integral that is actually integrable, that I can actually go out and integrate. All right, so now we're going to take a look at one that's somewhat different. If you notice before, we had integrals. These were our previous ones. We had the square root of a squared minus x squared, where the constant came first, right? We had the square root of a squared plus x squared, where x squared came second again. The constant came first, but it was addition. And now what you'll notice here is that this one is of this form. Okay, it's going to be the square root of x squared minus a squared. All right, where the constant comes second, where we're subtracting the constant. Now, what we're going to do in this case is we're going to utilize secant. Okay, we're going to utilize secant here. So I'm going to let x equal 2 secant theta. All right, and the idea that we're working with here in terms of the trig substitution is exactly the one that we've been working with before. So now this is going to give me, so x will equal 2 secant theta. Dx will then equal 2 secant theta tan theta d theta. Excuse me. So now I have the integral of 2 secant theta tan theta d theta. All right, make sure that you do substitute for dx, divided by the square root of 2 secant theta squared minus 4. And this is then going to equal the integral of 2 secant theta d theta divided by, or 2 secant theta tan theta d theta, divided by the square root of 4 secant squared theta minus 4. And this ends up equaling the integral of 2 secant theta tan theta d theta divided by, and this will be 2, the square root of 4, now tangent squared theta. And the reason why it's tangent squared theta is because this is 4 times secant squared theta minus 1. So that's that substitution again. This ends up giving me now the integral of 2 secant theta tan theta divided by tan theta d theta. Or excuse me, 2 tan theta d theta, because we've got the square root of 4. And this will then equal the integral of secant theta d theta. And that is simply the natural log of secant theta plus tan theta d theta plus c. So you can see, same idea that we're working with here. The whole idea is to make the substitution so that we can actually go in and transform our integral into something that I have an antiderivative for. Okay, that I can actually find the integral rather easily for. Now what I need to do is I need to figure out what secant theta is and what tangent theta is. Well, I know that x equals 2 secant theta. So I'm going to solve for secant theta. So secant theta equals x over 2. That's great. And now I'm going to draw my triangle to figure out what tan theta is. So if secant theta is equal to x over 2, that means that the adjacent, right, okay, because the adjacent is my denominator, is going to be 2, x is going to be my numerator, or excuse me, my hypotenuse, and then this is going to be the square root of x squared minus 2 squared, okay, which equals the square root of x squared minus 4 by the Pythagorean theorem, okay? Because remember, that's a right triangle. So tangent theta now is going to equal the opposite. It'll be the square root of x squared minus 4 divided by the adjacent, which is 2. So when I go back in, I'm going to substitute back into this function right there. That's going to end up equaling the natural log of the absolute value of x over 2 plus the square root of x squared minus 4 over 2 in absolute value plus c. And so again, what we've got here is we've gone in, we've utilized our substitution in order to make our function integrable. Once we've done that, then we can go in and resubstitute. Since these are trig angles, or since these are trig functions, we're going to have to utilize that right triangle in order to get the right things to substitute. So now our form here, this third form, is going to end up being the integral of the square root of x squared minus a squared. All right, so we're going to dx. We're going to let x equal a secant theta, and so dx will end up equaling a secant theta tan theta. Okay, when we substitute back in, we'll end up with the square root of a squared secant squared theta minus a squared d times a secant theta tan theta d theta, And so this will end up equaling the integral, and this turns into a squared tan squared theta. So this is a squared tan squared theta times a secant theta tan theta d theta, okay, which equals the integral of, and this will be a tan theta times a secant theta tan theta d theta, okay, which is just a squared, the integral of a squared secant theta tan theta, secant theta tan squared theta d theta, okay, which you could integrate. Or we might have, kind of a different form, right? Whatever it is, this just gives you an example of how to do the substitution. Now, what we also want to get is that in this case, since x equals a secant theta, all right, then that means that x over a is going to equal secant theta. And then we could draw our triangle to find any other angles, okay? What that triangle is going to look like is it's going to have the hypotenuse is going to equal x, the adjacent, okay, is going to be a, and then that opposite side is going to end up being x squared minus a squared using the Pythagorean theorem. So something like tan theta will end up equaling the square root of x squared minus a squared, all divided by a. And that is the general substitution for a function that has something of this form, like the square root of x squared minus a squared. What I'm going to do in just a second is I'm going to go through a couple of examples that don't look exactly like what we just did, okay? So you can see how it is that we're going to utilize the substitutions. So let's take a look at this kind of function, okay? Or this example, the integral of dx over the square root, dx over x squared times the square root of 1 minus x squared. And what I want to notice is that I have a term in the form of the square root of 1 minus x squared, which looks like the square root of a squared minus x squared, okay? And so if I have something in that form, what I know from my experience is I'm going to let, okay, right, since a equals 1 in this case, I'm going to let x equal sine theta, okay? X is going to equal sine theta because that's the proper substitution for something of that form, okay? So then dx is going to equal cosine theta d theta. So now I'm going to end up with, this is when I do my substitution, is going to end up being the integral of cosine theta d theta divided by sine squared theta times the square root of 1 minus sine squared theta, okay, which is equal to the integral of cosine theta divided by sine squared theta times the square root of now cosine squared theta d theta. And this will then equal, this is now cosine theta, the integral of cosine theta divided by sine squared theta times the square root of cosine squared theta, cosine theta. Now that I take it out of the square root, this will be just cosine theta d theta. And so this ends up being the integral of 1 over sine squared theta d theta. Okay? And that is the integral of cosecant squared theta d theta. So the antiderivative of cosecant squared theta d theta is going to end up equaling the negative cotangent theta plus c. So now I've actually got I've now integrated, I'm good. What I need to do now is I need to substitute for theta. So what I'm going to do is I'm going to let x, right, x equals sine theta. That's my original substitution. So when I draw my triangle, that's going to be, if this is theta, x is the opposite, and 1 is the hypotenuse, and so that means the adjacent is going to end up being 1 minus x squared, okay, using the Pythagorean theorem. So cotangent theta is going to equal the square root of 1 minus x squared divided by x. So my integral, my final integral, is of dx divided by x squared times the square root of 1 minus x squared, we're just going to substitute this in for cotangent, so it's going to be negative square root 1 minus x squared divided by x dx. So once again, same idea here. I had a form. I had the square root of 1 minus x squared. I know that form is a substitution for sine. So I go in, I substitute sine, and when I substitute sine, that allows me, after some algebra, okay, to find something that I can then integrate. I went in, I integrated, and then I have to go out and I have to substitute in for either theta or some trig function of theta. If it's a trig function of theta, I'm utilizing my triangles, right? Once I do that, I resubstitute back in and get values in terms of x. So now let's take a look at another example. And this one doesn't immediately look like anything that we would expect, right? If you look at it, it's like, oh, okay, well, there's like an x to the 6. What do I do with this? This doesn't have my form, right? But if I actually go through and do a bit of algebra, I can actually see that it will have one of the forms that I want. So let's say dx, and I'm now going to factor out x squared, an x squared term, and I'll end up with x to the 4th minus 1, okay? Which will equal the integral now of dx over x root x to the 4th minus 1, okay? And if I look here, this actually does have the form of something that I want, all right? So what I can do with this is actually, I can say, all right, well, I'll let x squared, okay, equal, in this case, secant theta. All right, and then I'll end up with a secant squared theta minus 1, right? Okay, secant squared theta minus 1, which is great. That's exactly what I want. The one thing that I'm going to need to do, though, is I'm going to need to take the square root, all right? Because I need a dx, all right, and I also want to know what my x is. So if I look here, I can let x squared equal secant theta, okay? And then I can go in and I can make the substitution by saying that x will equal the square root of secant theta. All right, so dx will end up equaling 1/2 the 1/2 times secant theta to the negative 1/2 times, and then the derivative of secant theta, which is secant theta tan theta. Okay, so what we end up with here when I simplify that is I get that dx is going to equal secant theta tan theta divided by 2 times the square root of secant theta, okay, which is actually equal to tangent theta, or excuse me, is equal to the square root of secant theta times tangent theta divided by 2. And the reason why we can see that is you can actually see, okay, well, if I take the square root of secant theta and I divide it into secant theta, I end up with secant theta to the 1/2, right? And that's just some algebraic simplification. Okay? We don't want to forget we got to add in our d theta. So there's our d theta. We'll have d theta at each step of the way. Okay, and there we are. So now we can actually make a substitution. Notice we still are utilizing that substitution where we plug in and we want to end up with secant squared theta minus 1. So what is the value that I need to plug in there to get secant squared theta minus 1? Well, that's going to be x squared equal to secant theta. So now I plug in my values. dx, right, is the square root of secant theta, okay, times tangent theta divided by 2 d theta, okay, divided by, all right, and remember this is going to be divided by the square root of secant theta times the square root of secant squared theta minus 1, okay. Oh, this is great news. If we look at this, or at least we look at this this integral, what's going to end up happening is that these secant thetas are going to cancel, all right. So we end up with the integral of, and this is now going to be tangent theta over 2, and this is going to be the square root of tangent squared theta d theta. So this ends up being equal to 1/2, or the integral of 1/2 d theta, because these are going to cancel out as well. And so this ends up equaling just 1/2 theta plus c. That's not bad at all. We could do something with that. Now, here's the thing, right? Okay, notice we've got x squared equals secant theta. So we need to find theta. So x squared is going to equal secant theta. All right. And I think what I'm going to do is I'm going to transform this into x squared equals 1 over cosine theta. Okay. Because generally we're not going to find secant inverse theta. We're generally going to go with the cosine inverse, tangent inverse, or sine inverse. Okay. So this will then give me x squared cosine theta equals 1. And so cosine theta equals 1 over x squared. And so theta will equal cosine inverse of 1 over x squared. When I plug that back in, what I get is I get that my integral, the integral that I had before, the integral of dx over the square root of x to the 6th minus x squared is going to equal cosine inverse 1 over x squared plus c. And that is my integral. So in this example, we had to work a little bit harder in order to see that we had that trig substitution. All right? And sometimes when you're actually going in and you're trying to integrate, that's what we have to do. We have to kind of work with things, see that we can transform things into the proper form so that we can then go out and integrate them. Okay? And then we see that there's a little bit more that we have to do in order to transform this back into a function of x. Okay? So that completes the lecture on trig substitutions. Trig substitutions, we've got 3 basic forms. Okay? We looked at those 3 basic forms. All right? And I'll rewrite them here for you. I have a form of a squared minus x squared. Okay? That substitution is going to have x equal to a sine theta. So that's that substitution. In addition to that, I'll have the square root of x squared minus a squared. That's going to have x equals a secant theta. All right, notice that the constant comes second there. And then I could also have the square root of a squared plus x squared, or x squared plus a squared, given that it's just addition. And that's going to have a substitution of x equals a tan theta. Okay? After that, we just got to go out and find dx. All right? When we're finished with our integration and our algebraic simplification, then what we need to do is go find theta or whatever values that we have for the trig substitutions. This completes the lecture.